Okay, I'd like to start off talking about differentiability with an example. So let's try to find f prime of x if f of x is equal to absolute value of x, which, just as a reminder, can be written as a piecewise function. It's equal to x if x is greater than or equal to 0. So if x is a positive number, the absolute value leaves it alone. And it's equal to negative x if x is less than 0. So if x is a negative number, it multiplies it by -1 in order to make it positive. Let's find the derivative at x equals 0. So if we use the definition of derivative, we have that f prime of 0 is equal to the limit as h approaches 0 of f of 0 plus h, which is just h, minus f of 0 divided by h. This is equal to, because we have different behavior if h is positive or negative, and recall that when we take a limit as h goes to 0, we have to take values both on the left and the right. So that means that h can have positive or negative values. So that means when we take this limit, we're actually going to have a limit of a piecewise function. So if h is positive, then we'll have h, f of 0 is 0, so that goes away. So h divided by h, which is equal to 1, if h is greater than or equal to 0, but it's negative h divided by h, which is -1, if h is less than 0. So if we look at this, if we come in from the right-hand side, then we have a value of 1 always, so the limit from the right is equal to 1. But as we come in from the left-hand side, we get a value of -1, so the left-hand limit is -1, and therefore the limits from the two sides do not agree, so the limit does not exist. So you might wonder what went wrong. We tried to find the derivative, and we got a limit that doesn't exist. And so the answer is that nothing went wrong. Sometimes functions do not have derivatives at certain points. And so this is a concept we need to explore further, because we don't want to waste our time trying to calculate a derivative if it turns out that the derivative does not actually exist. So we need to think about, when can this sort of thing happen? So first we need a definition. A function is differentiable at x if, let's say x equals a, if the limit as h goes to 0, f of a plus h minus f of a divided by h exists. So if we can calculate the derivative at that point and nothing goes wrong, then we call the function differentiable there. If this is true for every point that we pick a, then we just say it's a differentiable function. But for something like absolute value of x, we see that the function is not differentiable at 0. So there are basically 3 ways a function can fail to be differentiable. So the first way is if the function has a sharp corner, or what's sometimes called a cusp. So an example of a function like this is f of x equals absolute value of x at x equals 0. So if you plot that function, it looks something like this, and we can see at this point 0, there's a sharp change in where the direction the graph is going, so that sort of corner indicates the function is not going to be differentiable. Second thing that can happen is if the function has a vertical tangent line. So remember, the derivative gives the slope of the tangent line, so that's the value of this limit. So if the tangent line is vertical, then in in some sense that's like a line having an infinite slope, but of course that doesn't really make much sense because infinity is not a number. So in that case, the value of this limit would be infinity, and we say if the limit is infinity, then it does not exist. So in that case, the function would not be differentiable. So an example is the function f of x equals x to the power 1/3 at x equals 0. So let's see why this is. So if we take the limit as h approaches 0, f of h minus f of 0 over h, this becomes the limit as h approaches 0, h to the 1/3 over h to the 2/3, h. And then when you simplify that, you get limit as h goes to 0 of 1 over h to the 2/3. And so as h goes to 0, because we're squaring it, it doesn't matter if h is positive or negative, so we may as well assume it's positive. So this is some really, really small number near 0. The numerator is like a constant, so as we divide by smaller and smaller numbers, this will be approach infinity. So the limit does not exist, and the function is not differentiable. And so this function looks something like this. And we can see that at 0, the function is going basically straight up. It has a vertical tangent line, and that's what leads to this lack of differentiability. So the third thing that can go wrong is the function is not continuous. So of course, you've seen lots of examples of discontinuous functions. Let me just sketch a graph to show what's going wrong. Let's suppose we have a function like this, which has a jump in it. Let's suppose we want to find the derivative at 0. Well, it's the limit of the slope of secant lines. So here's one secant line. If we move the point closer, we get another secant line, and you see these secant lines keep getting steeper and steeper and steeper as we get closer to this discontinuity. So as a result, when we have this jump, when we take the limit, the secant lines will approach a slope of infinity, and therefore the limit does not exist. So if the function is not differentiable, if the function is not continuous, then it's definitely not differentiable because of this problem. And that's actually an important result. So a theorem is that if a function is differentiable at some point x equals a, then it is automatically continuous at x equals a. So every function, if it's differential at a point, has to be continuous. But the opposite is not true. So there are lots of functions which are continuous but not differentiable. And we've actually already seen two. Absolute value of x and x to the 1/3 are continuous but not differentiable at 0. So if the function is differentiable, it's continuous, but if the function is continuous, it might or might not be differentiable. Okay, so let's see a differentiability example. So let's suppose we have a function f of x equals ax plus b if x is less than or equal to 0, and it's equal to x plus 1 squared if x is greater than 0. And we want to find a and b, so f of x is differentiable. So the first thing to notice is that if we're not at x equals 0, then the function just looks like ax plus b. It's a straight line. We know it's differentiable. And similarly, if we're far to the right of 0, then we use this formula. This is just a formula for a parabola, and so of course that's differentiable as well. So the only problem is near where the formula changes. At x equals 0, this thing might not be differentiable unless we pick the right values for a and b. So the first thing is that in order for the function to be differentiable, we've already seen that it has to be continuous at x equals a if it's differentiable. So first, to make f of x continuous, we know that the value of the function at x equals 0 using this top formula has to match the value if we plug in x equals 0 to the bottom formula. So based on that, we can immediately see that the only way we can have this function be differentiable is if b is equal to 1. So next, we want to make sure that it actually is differentiable, so we have to just check the definition of derivative at x equals 0 and see if it exists and what value of a we need in order for the limit to exist. So let's look at the limit as h approaches 0 of f of h minus f of 0 divided by h. Well, since f of x is a piecewise function, this limit will also be a piecewise function. So if h is less than or equal to 0, we use this top formula here. So we know b is equal to 1, so f of h, if h is positive, will be h plus 1, but then f of 0 is just b, which gives us minus 1, divided by h. Then if x is positive, we use the bottom formula, and in that case we'll have, let's see, h plus 1 squared minus f of 0. We use the top formula, so that's still 1. Then we divide by h. So let's simplify this as the limit as h goes to 0 of this top one just gives us a value of a. The bottom one, if we expand it, we'll get h squared plus 2h. Then we have a minus 1 cancels with the plus 1 from expanding this square. And then we divide by h. So this is x less than or equal to 0. This is x greater than 0. So now we can simplify further. So if we cancel an h from this bottom thing and take the limit, then you'll see you get a value of 2. So this limit is equal to a if x is less than or equal to 0, and it's equal to, well, okay, let me put it this way. Let's keep the limit as h goes to 0. So it's the limit as h goes to 0 of a if x is less than or equal to 0, and 2 plus h if x is greater than 0. So if we take the right-hand limit, we'll use this formula, and we'll just get a value of 2. If we take the left-hand limit, then we'll get a value of a. And we want those two, the limit to exist, so the left-hand and right-hand limits have to match up. So that means that a has to be equal to 2. So this has allowed us to figure out the values of a and b, which make this function differentiable. And so if you were to look at the graph of this function, you would see that somehow let's see, so we have the slope the line is 2x plus 1. So that means it's a line that does something like this. And then you would see that on the other side, if x greater than 0 is the equation of some parabola, and because of the values we chose, it'll end up meshing together smoothly with that parabola, so there won't be any sharp corner or anything here. So if you have a piecewise function, you're not careful, you could get some sort of sharp corner here, or even worse, a discontinuity, which would keep things from being differentiable. So by choosing special values of a and b, we get it so that the two sort of mesh together nicely and we get a differentiable function.